Ever wondered why some machine learning models fail when confronted with unpredictable data? Picture this: you're training a system to predict house prices, but a few properties are worth millions while others are just a few thousand. This heavy-tailed noise, data with extreme outliers, can throw traditional methods off track. Today, we're exploring a groundbreaking study that reveals how ridge regression, a decades-old technique, can thrive even in these chaotic scenarios. It's not just about surviving outliers, it's about leveraging them to build more robust models. So what's the core idea? Ridge regression is a method to prevent overfitting by adding a penalty to complex models. Think of it as a balance: too much complexity and your model chases noise, too little and it misses real patterns. But here's the twist. This research proves ridge regression is minimax optimal even when data defies normality. Traditionally, models like this required sub-exponential noise assumptions, data that's well-behaved with no wild swings. But real-world data, it's often heavy-tailed, like financial markets or sensor readings with sudden spikes. The breakthrough: a mathematical tool called the Fuk-Nagaev inequality, which quantifies how extreme values impact predictions. By applying this to reproducing kernel Hilbert spaces, function spaces used in kernel methods, the researchers showed ridge regression can achieve the best possible error rates. Here's the kicker: their analysis works across finite and infinite dimensional features. And the results? They match the best-known rates from sub-exponential settings, but without those strict assumptions. Why does this matter? It means models can be more reliable in real-world applications. Think self-driving cars, medical diagnostics, or climate modeling, places where outliers are the norm, not the exception. This work is a step toward making AI more resilient to the messy, unpredictable data we actually encounter. So next time you hear about machine learning breakthroughs, remember, some of the most powerful tools are the ones that adapt when the data gets wild. And that's the story of ridge regression, reimagined for the real world. Thanks for watching. If you want to dive deeper into robust machine learning, hit subscribe for more explorations into the math behind the tech. See you next time. Ever wonder how your phone's weather app or a doctor's diagnostic tool makes accurate predictions? It's not magic, it's math. Today, we're unpacking a fascinating study that shows how scientists keep machine learning models from going off the rails. Spoiler, it's all about controlling errors, and the math behind it is wild. Let's start with a simple question: how do you know if a model is trustworthy? Imagine training a model to predict something tricky, like stock prices or disease spread. But here's the catch: data is noisy, models are imperfect, and errors happen. The key is figuring out how big those errors can get. That's where bounds come in. Think of them like a safety net. They guarantee predictions won't be too wrong with high confidence. The researchers break down errors into three components: I11, I12, and I13. Each represents a different type of uncertainty. First, I11, random fluctuations like static on a radio. To tame it, they use Bennett's inequality, a tool that calculates the maximum wobble in data based on sample size and a parameter called alpha, which controls model complexity. The bigger alpha, the simpler the model, the less it's tempted to overfit. Next, I12, data errors, flawed measurements, like a sensor giving a wrong reading. Here they turn to the Fuk-Nagaev inequality, a risk manager for outliers. It balances between rare disasters and everyday fluctuations, ensuring extreme values don't derail predictions. Finally, I13, model bias, the built-in mistake between predictions and the true answer. It's like a slightly off compass. Even with perfect data, the model might drift. But here's the kicker: as alpha decreases, allowing a more complex model, this bias shrinks, but only up to a point. Too small, and the model starts chasing noise instead of patterns. Putting it all together, these bounds show that with the right alpha, the model's error is tightly controlled. It's a balancing act, like tuning a radio. Too much static, high alpha, and you miss the signal. Too little, low alpha, and you're drowned out by noise. The math proves there's a sweet spot where predictions are both accurate and reliable. Why does this matter? It means models can adapt to real-world chaos without sacrificing accuracy. From autonomous vehicles to climate models, this research is a cornerstone for AI that thrives in uncertainty. The next time you rely on a machine learning system, remember, the math behind it is as resilient as the problems it solves. Thanks for watching. If you want to explore more about robust machine learning, hit subscribe for deeper dives into the math behind the tech. See you next time.